Scientists have made a groundbreaking discovery. They found a massive underground reservoir of liquid water on Mars. This reservoir is so large that it could cover the entire planet with water up to a depth of 1 to 2 kilometers, or about a mile. This discovery has solved a long-standing mystery about Mars. What happened to all the water? Mars wasn't always the dry, dusty planet it is today. Billions of years ago, Mars was a very different place. It had a thicker atmosphere and a warmer climate, allowing liquid water to flow across its surface. How do we know? Well, 3 critical pieces of evidence show water once flowed on the red planet. The first is a network of valleys and outflow channels. Mars is dotted with features closely resembling river valleys and deltas on Earth. These networks of branching valleys suggest that liquid water once flowed across the Martian surface, carving out channels and depositing sediments. The second is the presence of hydrated minerals. The detection of minerals that only form in the presence of water, such as clays, sulfates, and certain types of salts, provides strong evidence that water once existed on our neighboring planet. These minerals have been found by orbiters like the Mars Reconnaissance Orbiter and by rovers like Curiosity. Finally, Martian rovers have discovered sedimentary rock formations on the planet, similar to those formed by water processes on Earth. These layered rocks often show features like crossbedding, which occurs when water flows over a surface, and ripple marks created by moving water. But between 3 to 4 billion years ago, Mars experienced a series of catastrophic events that dramatically altered its history. The trouble began with the collapse of its magnetic field. Unlike Earth, Mars lost its global magnetic field relatively early in its history. This magnetic field, created by a dynamo effect within the planet's molten core, would have shielded the Martian atmosphere from the solar wind, a constant stream of charged particles emitted by the Sun. As Mars' core gradually cooled, the dynamo effect weakened, leading to the eventual loss of the magnetic field. With the magnetic field gone, Mars's atmosphere was left vulnerable to the persistent solar wind. Over time, this solar wind stripped away much of the atmosphere, causing the atmospheric pressure to drop significantly. As the atmosphere thinned, it became increasingly difficult for liquid water to exist on the surface. Water that might have once been present in liquid form began to evaporate and escape into space. The thinning atmosphere also led to a weakened greenhouse effect, resulting in a sharp drop in temperature. Mars transitioned from a warm and wet environment to the cold, dry world we see today. As the planet cooled, any remaining liquid water froze, becoming surface ice or permafrost hidden beneath the surface. But something didn't add up. If our theories were correct, even after accounting for the water lost to space, Mars should still have a significant amount of water. The frozen water in the polar ice caps wasn't nearly enough to account for it all. This raised the intriguing question: where is the rest of the water hiding on Mars? And if it still exists, could it potentially support life as we know it? The answer came from NASA's InSight lander, a groundbreaking mission that aimed to explore Mars's interior structure. Unlike previous missions focused on surface exploration, InSight was designed to dig deeper, literally and figuratively. Its mission was to investigate Mars's seismic activity, heat flow, and internal composition by looking beneath the crust. Throughout its 4-year mission, InSight detected more than 1,300 Mars quakes. These quakes originated from meteor impacts and rumblings from volcanic areas, all of which produced seismic waves that allowed geophysicists to probe the interior. Hidden within the signals of these seismic waves was a surprising discovery: a large reservoir of liquid water. The technique used to make this discovery is similar to what scientists use on Earth to study our planet's internal structure. By analyzing how seismic waves behave as they travel through different materials, seismologists can infer the properties of those materials. To locate this hidden Martian water, scientists applied a mathematical model of rock physics similar to those used on Earth to map underground aquifers and oil fields. The model revealed that the seismic data was best explained if, deep below the surface of Mars, there existed a layer of fractured igneous rock with its cracks filled with liquid water. Igneous rocks are formed from the cooling and solidification of molten rock material, either magma below the Earth's surface or lava on the Earth's surface. This process occurs in various settings, such as beneath volcanoes or as lava flows after volcanic eruptions. As igneous rocks cool and solidify, they can develop fractures and cracks. These fractures can create pathways for water to flow through the rock and be stored in the spaces between the cracks. Over time, these cracks can widen due to processes like weathering, allowing even more water to seep in. Though igneous rocks are not typically the most porous or water-retaining type, they can still hold water under certain conditions. While the discovery is essential in our understanding of Mars's water cycle, this layer is buried at depths between 11.5 and 20 kilometers or 7 to 13 miles, making it far too deep for future astronauts or current technology to reach. Even on Earth, drilling to such depths would be an extraordinary challenge. Although the existence of liquid water on Mars doesn't automatically mean that life exists there, it certainly opens up intriguing possibilities. The conditions within this underground reservoir could be similar to environments on Earth, where microbial life thrives, such as in deep mines or on the ocean floor. Researchers believe that if habitable conditions exist on Mars, they are likely to be found deep underground. This discovery suggests that understanding the Martian water cycle is crucial not only for grasping the planet's climate evolution, but also for assessing its potential to support life. If life ever existed or still exists on Mars, it might be hidden in these deep underground waters, waiting to be discovered. With the discovery of a massive reservoir of water on Mars, it's easy to imagine the red planet as a potential future home. However, setting foot on Mars is still a distant goal. There are 5 main challenges. One of the biggest hurdles is the sheer distance and the time it takes to get there. On average, Mars is about 225 million kilometers or 140 million miles from Earth. A round-trip mission to Mars would take approximately 18 to 30 months, including traveling to Mars, staying on the planet, and returning to Earth. Astronauts would need enough supplies to last the entire mission. The distance also means that help from Earth would be delayed by minutes, making immediate assistance difficult if any problems arise. The second problem is radiation exposure. Space is filled with harmful cosmic radiation and solar particles that can pose serious health risks to astronauts. On Earth, we're protected from much of this radiation by our planet's magnetic field, but Mars doesn't have a similar shield. This means that during the long journey to Mars and the time spent on its surface, astronauts would be exposed to levels of radiation that could increase their risk of cancer and other health problems. The third is the environment. The red planet has a harsh environment with surface temperatures that can drop to -125 degrees Celsius at night and only rise to about 20 degrees Celsius during the day in the summer. The planet also experiences frequent, often planet-wide dust storms that can last weeks or even months, potentially disrupting solar power generation and damaging equipment. Protecting astronauts and equipment from these extreme conditions is a significant challenge. The fourth is the life support system. Supporting human life on Mars requires reliable systems to provide air, water, and food. Unlike Earth, Mars has a very thin atmosphere made mostly of carbon dioxide, with very little oxygen and almost no accessible water. This means that astronauts will need advanced life support systems to generate oxygen, recycle water, and produce food on Mars, or bring enough for the entire mission. These systems must be extremely dependable because any failure in the harsh Martian environment could be life-threatening. Finally, we have the challenge of physical and mental health. Prolonged exposure to microgravity during the trip can cause muscle atrophy, loss of bone density, and other physical health issues. Once on Mars, The lower gravity, about 38% of Earth's gravity, may also have effects on the human body that we don't fully understand yet. Beyond the physical challenges, the psychological impact of such a mission is also a major concern. The isolation, confinement, and great distance from Earth could lead to stress, anxiety, and depression among the crew. Keeping astronauts physically and mentally healthy throughout the mission is a complex challenge that requires careful planning, ongoing support, and innovative solutions. The discovery of the water reservoir on Mars has added an exciting new chapter to our understanding of the planet's history. It opens up intriguing possibilities for future exploration, including the potential to tap into this resource. While this may be a distant goal, it sparks the imagination about what could be achieved as we continue to explore and learn more about Mars.